Two small, equally charged spheres, each of mass m, are suspended from the same point by silk threads of length L. The distance between the spheres x is much smaller than L. Find the rate dq dt with which the charge leaks off of each sphere if their approach velocity varies, as v is a over square root of x, where a is a constant. Okay, so what is happening? So we have this point from which two threads are hanging, and we have two spheres, and they each have a mass mg. They are x apart, and the length of the string is L. Now, each ball has the same charge, so that means they're going to repel. So we have the electrostatic force that's causing them to repel away from each other. Now, the charge is leaking, so the electrostatic force becomes weaker. And gradually, as the force becomes weaker, the balls are going to move towards each other, right? Closer and closer until they meet somewhere in the center, at which point they no longer have a charge, so they won't repel anymore. So we also have a tension force, right, from the string, right? And let's also draw the angle at which the string is holding the ball, which we'll just say is theta. So at this point, we can make a free body diagram for just one of the balls since they're symmetrical. So we have a downward force of mg, we have a tension force, and we have the electrostatic force. And I'll just make the reference frame so that the upward direction is positive y and to the right is positive x. And we can also draw this angle theta. So now let's just use Newton's second law to write out the sum of all forces. So the sum of all forces is equal to m mass times acceleration. And let's write it out for horizontal first. So what horizontal forces do we have? We have F in the negative x direction, and we also have the sine component of tension because it's across from theta. So we have F in the negative direction and the sine component of tension. Now, whenever we have leaking charge problems, we have to assume that the charge leaks very, very slowly. So in fact, it leaks so slowly that acceleration becomes negligible. It's essentially zero. We don't have any acceleration because the motion takes place over such a long time. We can also write out our y components. What y components do we have? We have the mg, the weight in the negative y direction. We also have the cosine of tension in the positive direction. So negative mg plus the cosine component of tension. And we don't have any acceleration in the vertical direction. Okay, another thing I want to address is that essentially the balls are going to move towards each other in more of this arc formation. They're going to follow this arc path. So why are we saying that the balls are moving horizontally? So this has to do with angle theta. So remember that x is much smaller than L. So if we draw this triangle where this is x and this is L and this is theta, if you just imagine this triangle, how it looks like as x becomes really small in comparison to L, theta gets really tiny. So we're just going to say that theta is 0. We're going to approximate 0, theta as 0. And the motion of our ball, like I said, it's going to follow more of an arc path. So it's actually going to be going more here. And this angle will also be theta. Now we can see how if theta becomes really small, essentially if it becomes 0, then this motion component doesn't really have any angle component. It is just going to be a horizontal line. Because if we took the cosine part of it, the cosine component of theta. Theta is 0, and cosine of 0 is 1. So we can just approximate it to be going in a horizontal motion rather than following the arc path, just because the angle is very small. Okay, so now using that information, we can continue to solve our system of equations. So let's solve y first. So if we solve for t, we have mg over cosine theta. We just said cosine theta is 1. So t equals mg. Now let's solve the x component. So F is the electrostatic force. Let me write that at the top. The electrostatic force, this is just Coulomb's law. Coulomb's law. Kq squared over x squared. Why is q squared? Because we have two charges. They have the same charge, q. X is the distance between the two charges. And k is a constant, 1 over 4 pi epsilon naught. Okay, so we have negative kq squared over x squared. We know that t is mg. What is sine theta? Sine theta, we need to look back at our triangle. So if this is x, that means that this is x over 2. So this is x over 2. That means sine is opposite over hypotenuse. So opposite is x over 2, hypotenuse is L. So we can write sine theta as opposite over hypotenuse, x over 2L. So let's write sine theta, let's just write that as x over 2L equals 0. Now let's continue solving this equation for q. Okay, so if we move everything else to the other side, right, we'll get q squared equals mg x over 2L times q squared over x squared over k, which is mg over 2lk x cubed. And if we square root both sides, q equals mg over 2lk to the power of 1/2 and x to the power of 3/2. Now we can also use our velocity, the information we have about velocity. V equals a over root x. So by definition, velocity is the first derivative of position. So dx dt is the same thing as velocity, which was a over root x. And we were also looking for dq over dt, right? That's what we were trying to find. So let's differentiate both sides of this equation with respect to t. So dq over dt equals, all of this is a constant, and then we can differentiate x, and we know what dx dt is a over root x. So root x actually just cancels out. Now let's rewrite this. dq over dt equals, we have 3 over 2a, we have a square root, we have 1 over 2k, we have mg over L. And k was 1 over 4 pi epsilon naught. So this becomes 3 over 2a root 4 pi epsilon naught. And 4 and 2 just cancels to get us 2 pi epsilon naught mg over L, everything square root, times 3 over 2a. And if you check at the back of the book, this is the right answer. All right, thank you.